Hi friends, welcome back to another episode in my series The Raytracer Challenge by James Buck, where I implement in Rust, a language which I'm learning while doing this series, a raytracer based on the book you see here in the browser. You can follow along by either joining me for this weekly published coding sessions or by checking out the code repository, which is linked in the show notes below. If you like these videos or other videos on my channel, please give them a thumbs up and subscribe to be informed when the next one comes out. Giving the video a thumbs up really helps, so please do so if you like it. In the last session, we actually implemented animation. We created the needed code in order to animate our scene, where we used the camera module which we implemented in the session before. Before going along and implementing the next part of this series, which is shadow casting and ensuring that our objects cast shadows into the world, let's just check what we have done the last time and to make sure that everything is still working. Quickly building the application. There we are. So let's take a look. Open output PNG, and let's see, let me move this into the capture area, and that is the scene we actually rendered the last time we rendered a static image. The last session was rendering an animation which looked something like this. I, by the way, added all the renderings we have done so far, as well as the animations, to the GitHub repository as well, for you to be able to easily download it should you want to just take a look at them. That's actually our animation we implemented the last time. The light is rotating around the objects and the spheres are moving around. But as you can see, unfortunately, there is absolutely no shadows whatsoever which are cast by the objects. And that is something we are going to change now while we are implementing chapter 8 of the book. So let's go ahead and do so. But before we can do this, we need to ask ourselves the question, how actually are we going to implement this? Once we have thought about this, it's actually quite easy to do so. But first, I want to explain to you what we are now going to do. Let's assume we have our eye somewhere here in the scene, and it's looking at something. Here's our eyeball, and it's looking at a sphere. Let's say the sphere is over here. And this sphere is to be looked on by this eye, so by our camera. And therefore we are currently calculating, or we are sending this ray into the scene, and we are calculating the intersection at this point with the sphere, and therefore calculating the geometry to be rendered. And we have furthermore, somewhere here in the scene, we have a light which is emitting some light, and it's there, and therefore it's casting its light rays onto this as well. So what we are currently doing in order to calculate the lighting of the spheres and of the scene, if you remember the chapter where we implemented Phong lighting, is we are actually calculating 3 different kinds of lighting information. We are calculating ambient light, which is the light that is there every time and always, so it's not dependent on any kind of light source. It's just the surrounding light which is always somewhere in the scene. Then we have the diffuse component, which actually depends on our light source directly. So it's calculated by using the vector from the intersection point to the light source, and we are seeing if there is some sort of direct possible way which the light source could hit this object, and at which angle it is hitting this object, and therefore we are calculating the diffuse lighting. And then in the end we have specular lighting, which is if the light source is reflected into our eye. So we are actually calculating the reflection vector and checking if light from the light source is reflected into our eye. And if it is, we have this specular component as well. And after adding all those components up, so ambient plus diffuse plus specular, we actually get our current lighting calculation. If we now want to introduce shadows into the calculation, we need to check if there is an object somewhere between the light source and our object. So we essentially need to ensure that, let me quickly remove this, that if there is such an object between our light source and the object we are casting a ray to, that then the light cannot hit this point. So if this is the case, we only got the ambient here, but we don't have the diffuse or specular lighting because the light source obviously is not capable of illuminating that specific intersection point of our scene. Actually calculating this is essentially quite easy because we already can check the intersection between objects or the world and rays. We only need to check this specifically for the ray which originates essentially at the intersection point and goes to the light. And if there is something in between this intersection point here and the light source here, which is in our case this object here, then this intersection point is in shadow and we need to only use the ambient light information and not the diffuse and the specular one. If there is nothing in this path of the ray, then we actually use the ambient, diffuse and specular information as before. Implementing this is not that hard because we have everything there to do this. Before we are even implementing the complex part where we actually use and calculate this second ray and this specific intersection for shadows, this ray casting, we are casting a shadow ray to see if the intersection is in shadow. Let's first implement what the actual rendering of this would be if we already knew this information, because it is quite easy to do so. If you remember, we implemented this material and we implemented the Phong material here before, which actually is an implementation of the Phong lighting model, which I just described with ambient, with diffuse lighting and with specular lighting. And we are calculating everything of that together here. We are casting the corresponding, we are casting the corresponding vectors and calculate the reflections and so on. And we are then correspondingly painting this pixel. But in order to be able to now implement this in a way we later on like, with shadow, we first of all need to extend this trait we created here, this illuminated trait, by not only being given the light which should be used, the position of the intersection, the I vector and the normal vector, but also another Boolean option which tells the renderer now, the material to render, if it should render something in shadow or not. Because being in a shadow situation is not handled by the material itself. It is handled at the level above, which creates the intersection calculation itself. We are actually adding an in shadow here and telling the system it is bool. Of course, now we can't implement this anymore because I've already changed this, if I've seen right, in the implementation. I should have changed it here first. So let's do this here in shadow Boolean. So now this implementation is okay, but now we need to pass it along here in shadow. And now the specific implementation here does need to know if something is in shadow. So let's put that in there as well. And now what I've said before is, if we are in shadow, we actually only need to calculate the ambient lighting. Everything else is no longer needed because it can't be properly calculated, as there is an object between the light source and our intersecting point. We essentially can directly go ahead and after this say if in shadow, we simply return the ambient light. Do I need a return here specifically maybe? Okay, it needs a return there. Okay, so now what we have done is if this rendering is in shadow, we only want the ambient light, and we have already calculated it at this point, so we don't need any further specular or diffuse lighting calculation, which even actually makes the rendering faster at the point where we are in a shadow. Of course, we are essentially making our whole renderer, our whole ray tracer slower now by implementing shadows, because we need to cast extra rays in the direction of the light source to see if there is and calculate intersections to see if there is another object in between the light source and the point we are actually calculating at the moment. So now that we have added this in shadow variable here, let's add another test, as we are always doing. First of all, let's fix our current tests, because now all of those shouldn't be in shadow. So let's add that all of those are not in shadow currently, so that we can still use those. Now we have fixed the test. Let's see, where else did we use this? Of course, the lighting uses, the world uses this to calculate the color at a specific for a specific ray. So in this case, let's just for now add an in shadow false there, so that the renderer still works. And after we have changed something like this, let's run the tests, of course. Why would I run the tests in release mode? That doesn't even make sense. Okay, so we have another, we have usage of chapter 6, which now uses this lighting calculation here. So let's add a false here as well. And now let's run the test, and everything compiles and the tests are still passing. So this is good. So our refactor didn't make anything bad or worse. Now let's add essentially a test for the material, which tests exactly this fact that we can now give the material the in shadow flag, and that it then only calculates the ambient lighting. So now that we have our test, let's run it and see if we did the implementation correct. And it seems we have. So this is good news. So now our material can render something in shadow. But of course now we need to implement to check whether something is in shadow or not. And we are using exactly this concept here, which I've explained before, to do so. Therefore, let's see, where is our calculation? Of course, it is within the world, because in our world, I guess, we have this color add implementation, and our color add implementation should exactly be what we want to look at, I guess. So we could either implement this within this function, or we could create another function, which we then use to calculate this. In order to have this a little bit more readable, I guess we will create a new function, which we could call, it doesn't need to be public, but we could call it isShadowed. This is actually exactly the name the book suggests for this function. So let's give it a self-reference there, because we need to reference the world, of course, to do calculations. And let's give it a point, which in this case is a position, I guess. It's the position. Yeah, it's the position of the hit we want to calculate. So it's used this position, which is then a tuple, of course. and we are returning a Boolean just to indicate whether something at this position inside this world definition is within shadow or not. Okay, we seem to need to import tuple here because we don't have it in this scope, which is okay for me. So now we need to implement the isShadowed function. Let me scroll it up here so that you can see it better. First of all, we need to calculate this vector here, the vector from the intersection point to the light source, which is quite easy. So we can calculate this vector and call it maybe shadow vector. So let's call it shadow v equals the lighting position, which we can actually access using self because it is stored there. So let's get the first light there. Once we are going to support more than one light, we of course need to do this calculation for every light in the scene. So we need to cast a shadow ray to every light in the scene and then combine those calculations intelligently, but it's not a problem. For now, we are only using the first light in the scene because for now we are only supporting one, and we are actually subtracting the position there. So after we have done this, can I subtract tuple from point light? Yeah, of course I cannot, because I need to get the position of this point light. Now that we have calculated this vector, we have the vector from the intersection point here to our light source. After that, we are calculating two further information from that. First of all, we are calculating the distance between the original point here, the intersection point, and our light source. Why we need this will become clearer in a second. We are calculating the distance by simply taking the shadow vector and using its magnitude for that, because that is essentially the distance from this point to the other. Then we need the direction, the normalized direction of this vector, just in order to create a ray from this point to the light source to see if there is something in between with which it intersects. So let's calculate the direction as well, which is then the shadow vector normalized. So now that we have distance and direction, we can actually create the corresponding ray, the shadow ray. And maybe I will really want to call this shadow vector just for clearance here, or for more simplicity, that it is rightly named. So now that we created all of those information, let's calculate the shadow ray, which is then quite easy. We can simply call ray new and give it the origin, which is the position we have, our intersection essentially, and our direction. So now that we have this ray, we can essentially go ahead and intersect this with our world to see if there is any object in our world which fulfills this condition here. So self.intersect with our shadow ray, and let's store this in, how did we call it before? Because it is not, it might be a hit, but it is not, yeah, it is not a hit, it is an intersection, that is right. So let's give let's get those intersections. It's not even only one, it may, there may be more than one in there. So now that we have those intersections, let's check if this ray even have any intersection. And we can do this as we do it always, by checking if we really got a hit back. And if we got a hit back, we can use it for something. Otherwise, if we don't have become a hit back here, we can always return false, because that is the default. If none of our calculations match anything, or there is nothing in between, the calculated, or the processed intersection is not in shadow. So let's just return this there. And I guess Clippy will warn us anyway, so maybe just do a false here. And now let's see. No, this is not, this needs to be XS hit. So we are getting the first hit of this ray. And now there is one thing we need to do, which we don't need in the calculation of the normal hit, because if we are casting a ray to calculate the color to see if there is a hit with anything in the world, we actually only need this information from the starting ray of our eye. Is there anything in the path to infinity? In this case now, we need to know if there is something in between the intersection point here and the light source. If, for example, the object would be here somewhere, this line would intersect with that and we would have a hit, but it would not interfere with our shadow. So we need to make sure that the hit lies between our hit here, our intersection here, and our light source. And in order to ensure that, we just need to check that the hit we got, which has the t value, which essentially is where along this ray did it hit, needs to be smaller than our distance value we calculated before. And this is essentially the reason why we calculated this distance value before. When I said it will get clear why we need this. We need this to ensure that we are within this range when calculating the shadows. So if this is actually the case, the t value is below the distance, then we have a true here, and otherwise we do not. So I need a return here, I guess. Yeah. So now that we have this shadowed function here, and we can calculate if something is in shadow, if a specific intersection, a point we are calculating is in shadow, we can now add this to this color add function here and use this to determine for every point we are calculating, for every pixel we are calculating, and every array we are shooting through the scene, if this one is in shadow or not. So let's quickly do this. Let is in shadow self is shadowed. And we of course need just take the position for now of our intersection, which we already use for our other lighting calculation here. We calculated it before here in this getComputed function. And then we just pass this information through to the rendering function. And now we actually should be finished and should have shadows in our scene. And I can tell you now that this will not 100% work, but it should produce, if we did everything right, a quite interesting result. So let's run our chapter 7 binary. Did I have? Yeah, I have a typo there. And let's do it in release mode. Otherwise, the rendering takes too long. And let's see what is the result now if we render our scene like this. Because, as I've said, it's quite interesting. There we are. And as you can see, we have shadows casted. But we have something quite strange going on here, because our whole scene seems to have random pixels which are now in shadow. So we do not only have those shadows, which are looking quite nice actually and quite correct. They are casted shadows by the light, quite hard casted shadows, and we might tackle this later once we are finished with the book. There is, of course, a way to create soft shadows in ray tracers as well, but we will not cover this at this point. But we have this whole picture containing of a lot of speckles here which are dark and do not seem to belong there, where obviously the calculation thought something is in shadow but is not. This effect is actually called acne. It's an effect which has a name because it is so common and happens so many times, and it's caused by a quite interesting effect. The reason is actually quite easy to understand. Let me quickly start a new drawing here. If we have this sphere, we have our eye here, and we had our light somewhere here emitting rays. So now we are projecting into the scene this ray, and we are calculating this intersection point here. Then we might actually have a problem. We might get this intersection a little bit too low within the sphere due to the simple problem that there are rounding errors in floating point calculations a computer makes. So we might be just be on this side of the sphere, but we could be just on this side of the sphere. And if we are actually on the inside of the sphere, then of course there is something in between the light source and our intersection. It's the sphere itself, or it's the object we are intersecting with itself. And this is actually what happens if we take a look at this picture here again. This is essentially what happens here, that for some of those calculations, the floating points aren't precise enough to be exactly on this intersection, on this surface, but they are slightly below. And because they are slightly below the surface, they are rendered like this, because the shadow now, that there is now the object itself in between the light source and this casted ray. As we now know this, we can actually fix it quite easily. Let me put away my tablet here again. We simply need to adjust the position of our intersection a little bit, or to provide an intersection point which is just above the surface and not directly on the surface, to make sure this strange effect does not happen. And essentially we have this computed intersections here created a couple of sessions ago, where we pre-compute information, or better said, where we store pre-computed information. And now we are going to not only store the point here, but we are going to compute here the overpoint, which is actually just a point as well, so a tuple. And this overpoint is then exactly what I just described. It will be just above our intersection. Just a little bit, an epsilon, a very tiny amount, essentially the same amount that we use in our fuzzy equality calculations here, this epsilon here, to ensure that two floating point values are equal, because that is exactly the amount which we might have in difference there. So now that we have this overpoint here, let's add it here as well. We of course need to provide it during the creation. And where is it? It is here in our intersection. We are here calculating this information. So in this get computed, we are calculating all those informations. And now we simply need to do the following. How do we calculate it? It's quite easy actually. Let's say the overpoint is the position which we already have moved into the direction of the normal vector, so plus our normal vector, which we already correctly calculated here, even if it's inside the sphere, so we actually already know on which side we are. So let's check here, And let's ensure that we add this normal vector and just multiply it with our epsilon value. Now let's check if we do it with this epsilon, if then our calculation is correct and our shadows are right and the acne is gone. So let me open up this output PNG, and yeah, it looks perfect. We now have implemented shadows, and I really much like this. This is absolutely awesome. Yeah, we are essentially finished with this chapter now. I will add the corresponding unit tests just to make sure that in the upcoming refactorings we are not damaging something off camera, as it is, I guess, not very interesting for you to see me writing tests. So if you are interested in them, they will be in the GitHub and you can take a look at them. But yeah, essentially we are finished. So this chapter has been done quite easily and quite fast. But now we can do something else. Remember that we implemented before animations with rotating light. So yeah, now that we have shadows, this should look really, really cool. So let's create one. There we go. Let's render our animation. There we are. Rendering is finished now. So let's quickly combine up everything using FFmpeg. There is something happening that I would not have expected. Let me make this a little bit smaller. So what we are doing now, actually, let me play this again. What's actually happening here now is, can I make this? What's actually happening here now is that the light is blocked by our walls. So the whole scene is casted into a shadow then, and so it's getting very dark because the light is behind our back walls when it's rotating around. That's something I wouldn't have expected, actually. But yeah, we have implemented it this way. So the light is actually too far away from our spheres. But we can of course change this. So maybe we should change this. But I like what has happened there. So maybe let's copy this and create create the file here, the copy, and let's call it chapter 8 animation. And now we are going to, where are we moving the light, or where are we positioning it? The moving is actually okay, and the positioning is not that great. So we need to have it maybe, I guess we are positioning the walls around the, where are we positioning the walls? We are positioning them at Z distance of 5, but the light, yeah, the light is positioned, if we are rotating it around, it's at a position of 10. If we have a static scene, this is not a problem, because it is lighting the scene from the front and therefore not encountering any problems with the wall. But now we actually need the light to be a lot nearer there. So maybe we could move it like, for example, 2. I'm not sure that I'm not hitting now a sphere and positioning the light into a sphere, which wouldn't be a good idea. So maybe let's quickly check where the center sphere lives, because I'm not 100% sure. So we have the left sphere, the middle sphere actually has linear scale. No, that's the transformation. We are moving it, yeah, and we are positioning it at yeah, 1, and where do we actually scale it? Do we scale it? Has it a size of 1? It has a size of 1. Okay, so this should actually work if we have this at the maybe. Let's see where we need to position it. We could, yeah, we could move it up higher, I guess, because having it higher should not be a problem. It only makes the light to shine more from above. So yeah, let's see what happens if we actually move it there. So rendering is finished. So let's create the animation again, and let's see if this time we are not hitting the walls while we are calculating, or we are not going beyond the walls. Let's see. Yes, finally. And as you can see, this looks quite fantastic as the shadow moves when the sphere goes up, and the shadow here moves while the light is rotated and the sphere actually is moved to the side. This looks quite amazing, and you can even see that we did it correctly, because now this green sphere here is starting to cast a shadow on the orange one at some point. Let me start this from the beginning, and let me make this a little bit bigger so you can can see it better. So there now comes the point, there you have it, where the green sphere casts a shadow on the orange one. And if this doesn't look great, I don't know what does. So now the scene is a lot more lifelike, as we can now see where something is actually positioned, because we can see its shadows. Yeah, thank you for joining me in this session here, where we implemented shadows for our ray tracer. And as you have seen, shadow casting isn't that hard to understand, and it's not that complicated. We will at some point, I'm quite sure, come back to this and implement soft shadows, even though this is not part of the book. But at the moment I'm having so much fun doing this and implementing this, I guess I will continue implementing things for this ray tracer once the book is finished. It is only a very nice guide to go along and implement all the needed different parts in the correct order to present and show. In the next session, we will actually implement another shape. Until now, we only have spheres, and in the next session, we will start implementing planes, which will be the next primitive body type we are going to implement there, so that we don't need to cheat and flatten those spheres to have a border, to have a floor and sides, but to really use infinitely large planes which are at those positions in the correct way. Thanks again for joining me, and please, if you like this video, give it a thumbs up. It really makes a difference for others to find this video as well, and for myself to see that you really liked it. Comment and subscribe if you want to know when the next one is published as well. And yeah, leave me a comment if you have any questions, as others did, or just to tell me what is good and what is bad. I really like this. And don't miss my other video series, which I have just started last week, which is called Quick Bytes. It will be a collection of short videos, mostly all below 5 minutes, 10 at most, which will introduce a specific concept, a language feature, or a tool, not specifically to Rust, but to everything that has to do with computers and that has to do with development of software, which I encounter in my day-to-day work and my hobby tinkering. So yeah, please check this out as well. I hope you enjoyed this session, and I hope to see you in the next one. Bye!